Hey everyone, and welcome to today's Explainer. So today we're going to dive into the fundamental physics that literally govern absolutely everything around us. I like to think of forces as these invisible hands shaping everything we see and do. I mean, even right now, just sitting there, you're interacting with multiple complex forces. You can't see them, right? But you can definitely see what they do. So we're going to pull back the curtain today and figure out exactly how these invisible hands push, pull, stretch, and spin our entire universe. Okay, so here's our roadmap for this explainer. We're going to cover 1. The effects of forces, 2. Stretching springs and proportionality, 3. Resultant forces and motion, 4. Friction and circular motion, and finally, 5. The turning effect. Let's jump right in. Section 1. The effects of forces. So, have you ever actually stopped to wonder what makes a massive traditional kite, like a wow balloon, lift up into the sky? A huge kite like that just simply won't fly if the wind isn't strong enough. Or think about a moving car. What invisible intervention is actually causing it to slow down and stop at a traffic light? Well, these everyday examples show us exactly how forces act on the world around us. A force is basically just a push or a pull, and it has two main categories of effects. First, it can change size and shape. Think of a chef stretching out a huge piece of pizza dough, or a hand pulling back the rubber band of a catapult. Second, a force can change motion. It can alter the direction of a moving shuttlecock when you smash it with a badminton racket, or it can hit the brakes to slow down a speeding car. So size, shape, and motion. That's essentially the physical footprint of a force. Moving on to Section 2, stretching springs and proportionality. Let's look at some raw data here to really build our understanding. Imagine we've got a spring hanging from a stand. With no load on it at all, 0 newtons, its original length is 16 centimeters. Now, take a look at how the extension increases so consistently as we add heavier loads. We add a 1 newton load and it stretches by 2 centimeters. Jump down to a 5 newton load and the spring extends by exactly 10 centimeters. You see it? There's a totally predictable rhythm happening here. And what's super interesting is how that raw data forms a perfect straight line that passes right through the origin. When we plot the load on the vertical axis against the extension on the horizontal axis, we don't get some random zigzag. We get this beautiful, direct line. This essentially proves that load is directly proportional to extension, meaning as long as the load isn't too heavy, doubling the force will exactly double the stretch. It's that simple. So the crucial takeaway here is this formula, K equals F over X. The K stands for the spring constant, and it represents the stiffness of the spring itself. It tells us exactly how much force in newtons we actually need to stretch that spring by a single meter or centimeter. A stiffer spring is going to have a much higher spring constant because, well, it demands way more force to stretch, which makes total sense, right? That's exactly why car suspensions use entirely different springs than the one inside your clicky ballpoint pen. But here's where we kind of have to ask a very practical question. What happens to the spring when the value of the load, that force F, becomes too large? Because springs aren't magic. They're made of physical metal, and they definitely have physical limits. Notice how when the force gets too high, that perfectly straight line suddenly curves downwards, hitting what physicists actually call the limit of proportionality. Up to that point, the spring behaves perfectly, stretching proportionally. But the second you cross that invisible line, the spring constant completely breaks down and your spring is permanently deformed. Yikes. Section 3. Resultant forces and motion. I really want you to keep this definition in mind because rarely is there only one single force acting on an object at a time. Like right now, gravity is pulling you down into your seat while your chair is actually pushing you back up. The resultant force is just the net result of all these competing pushes and pulls combined into one single overall force. Let's quickly break down how we calculate that resultant force without making it overly complicated. First, you just identify every single force pushing or pulling the object. Second, because forces always have a direction, you pick one way to be positive, which naturally makes the opposite way negative. And finally, you literally just add those numbers together. Let's look at some opposing vectors in action here to make it crystal clear. If you've got 3 newtons and 5 newtons both pulling to the right, they just team up for a resultant force of 8 newtons. Easy, right? But if you have 10 newtons pulling left and 6 newtons pulling right, they're fighting each other. So if we assigned right as positive and left as negative, you've got a positive 6 plus a negative 10. That leaves you with a resultant force of negative 4 newtons, which just means a net force of 4 newtons to the left. Which brings us to one of the most famous equations in all of physics, F equals ma.
Resultant force equals mass times acceleration. This equation tells us exactly what that resultant force actually does. If you apply a net force to an object that has mass, it is going to accelerate. And crucially, it's going to accelerate in the exact direction of that resultant force.
So let's contrast these two states. If forces are balanced, meaning the resultant force is absolutely zero, the object's motion doesn't change at all. If it was sitting still, it stays sitting perfectly still. If it was already moving at a constant speed in a straight line, it just keeps moving perfectly at that speed. But if the forces are unbalanced, meaning there's a net force left over, that's when you actually get a change. The object is going to either speed up, slow down, or completely change direction.
Section 4. Friction and circular motion.
You can think of friction as the ultimate resistor. It's a force that specifically acts in the exact opposite direction to an object's motion. It constantly impedes movement, which is exactly why things eventually stop rolling on their own. It produces heating, too. Just rub your hands together really fast and you'll immediately feel that thermal energy. And friction isn't just a thing for solid objects rubbing together. When an object moves through liquids or gases, friction acts as drag, sort of like the air resistance slowing down a descending parachutist. Now, let's talk about circular motion. The crucial point here is that to keep an object spinning in a circle, you absolutely must have a continuous force pulling inward. See, according to Newton's laws, objects naturally want to travel in a straight line. So to make an object curve into a circular path, a force has to act at a perfect 90-degree angle, perpendicularly, to the direction the object is trying to travel. Without that inward perpendicular force, the object would literally just fly off in a straight line. Which, by the way, is exactly why cars skid off icy, curved roads when their tires lose friction.
Section 5. The turning effect.
This next concept explains why it matters exactly where you push or pull an object. In physics, we actually call this the moment of a force. A moment is really simply the turning effect a force has around a fixed pivot point, or a hinge. Just think about opening a heavy door. You instinctively grab the handle on the far edge, right? You don't try to push it right next to the hinges.
And the math behind this is beautifully simple. The turning effect, the moment, is just your force multiplied by your perpendicular distance from the hinge. We measure it in Newton meters. This essentially means you can create a massive turning effect either by pushing really, really hard or just by moving much further away from the pivot point. Basically, distance is a multiplier of force.
Let's actually test this out and apply the formula to a real-world problem from our source material. Say a heavy door needs a minimum moment of 20.5 Newton meters just to open. If your arms can only manage a pull of 50 newtons, how far from the hinge must you place the handle? Well, because moment equals force times distance, we literally just divide the required moment of 20.5 by your force of 50. The answer? You need to place the handle at least 0.41 meters away from the hinge to get enough leverage to open that door. So, we've covered how forces stretch materials to their breaking points, how resultant forces govern absolutely all acceleration, the heat of friction, the perpendicular pull of circles, and the powerful leverage of moments. Which leaves us with this final thought. If invisible forces are constantly stretching, moving, and turning everything around you, what resultant forces are acting on you right now, and are you truly in equilibrium? Keep looking for the invisible hands in their world. Thank you so much for joining me on today's Explainer, and I'll see you next time.